There is a picture of the solar system that most of us carry around in our heads without ever really questioning it. The sun sits in the middle, and around it, in careful rings, drift the planets. Mercury, Venus, Earth, Mars, then the gap where the asteroids live, and then the giants, Jupiter, Saturn, Uranus, and Neptune, with maybe a small dot for Pluto trailing along at the end. It fits neatly on a page. It looks complete. And it is almost entirely misleading, not because any of it is wrong, but because of what it leaves out. If you tried to draw that solar system to scale, with the sun as a dot in the center and Neptune's orbit marking the edge of your paper, you would have drawn something like 1% of the actual structure. The rest, the other 99%, is a region so vast, so cold, and so quiet that it barely resembles the tidy diagram we grew up with. It has no color in most illustrations. It rarely appears in textbooks meant for a general audience. And yet, it is the true edge of our solar system, the place where the sun's gravity finally gives way to the rest of the galaxy. It is called the Oort Cloud. Tonight, it might be nice to spend a little time out there. Not the crowded, well-lit region near the sun, with its rocky little worlds bathed in warmth and light, but the vast, dark shell that surrounds all of that, cradling the entire planetary system the way a distant reef cradles a lagoon. It's a strange, silent place, and getting to know it changes how the whole solar system feels. The first thing to set aside is the shape. When we picture the planets, we picture a disk, because that's what they are. Mercury, Venus, Earth, Mars, and the rest all circle the sun roughly on the same flat plane. The way ripples spread out flat across the surface of a pond. It's a shape that makes sense because it comes directly from how the solar system formed, out of a spinning, flattening disk of gas and dust. The Oort Cloud does not share that shape. It isn't a ring, and it isn't a belt. It is closer to a sphere, or perhaps more precisely, a thick spherical shell wrapping around the sun and all the planets from every direction at once. Above, below, to every side. If you could rise up out of the flat plane of the planets and look back, you wouldn't see the Oort Cloud thinning out or disappearing the way the asteroid belt would. You would still be inside it, or approaching it, no matter which way you turned. In a very real sense, our whole familiar solar system, planets and all, sits like a tiny seed at the center of an enormous hollow ball of ice. The scale of that ball is difficult to hold in the mind, because the numbers involved stop feeling like numbers somewhere along the way and start feeling more like abstractions. Astronomers get around some of this difficulty by using a unit tailored to the solar system itself, called the astronomical unit. One astronomical unit is defined as the average distance between the Earth and the Sun, which comes out to about 93 million miles, or roughly 150 million kilometers. It's a convenient stand-in for a very large number, and it lets astronomers talk about the outer solar system without constantly rattling off strings of digits using that unit. Neptune, the outermost official planet, orbits the Sun at a distance of about 30 astronomical units. That is the traditional edge of the planetary neighborhood, the boundary most solar system diagrams quietly stop at. The Oort Cloud exists in an entirely different category of distance. Its inner edge is thought to begin somewhere between 2,000 and 5,000 astronomical units from the Sun, and it's believed to extend outward to somewhere between 50,000 and 100,000 astronomical units. At the upper end of that estimate, the outer boundary of our own solar system would sit nearly halfway to the nearest other star, Proxima Centauri. It helps, as with a lot of astronomy, to shrink the whole thing down into something a human body could actually walk through. Imagine scaling the solar system so that the distance from the Earth to the Sun is exactly 1 inch. On that scale, Neptune would sit a little over 30 inches away, well within reach of a large dining table. Pluto, still commonly pictured as marking the edge of things, would be about 40 inches out, just past the far edge of that same table, the Oort Cloud. On this same 1 inch per astronomical innate scale, would not even begin until you had walked several hundred feet away from that table. Its outer edge would lie somewhere around 1.5 miles away. The entire familiar solar system, sun and planets and all, would be a small cluster of specks sitting at the center of a sphere more than 1 mile wide. Everything we call the solar system in ordinary conversation, every world we've ever sent a spacecraft to, occupies a space that, on this scale, would fit inside a single room. The true boundary of our system lies out past the edges of a small town. This immense structure is not perfectly uniform throughout. Researchers generally describe it as having 2 connected regions rather than one simple shell. The portion closer to the planets, often called the inner Oort Cloud, or sometimes the Hills Cloud, after the astronomer who first proposed its existence, is shaped less like a sphere and more like a thick disk or a donut, still centered on the Sun but flattened compared to the region further out. This inner region is thought to contain several times more material than the outer portion, perhaps around 5 times as much, packed into a comparatively smaller volume, moving further out. The shape gradually transitions into the outer Oort Cloud, the true spherical shell that gives the whole structure its name and its defining feature. It's this outer region that surrounds the solar system uniformly from every angle. And it's the behavior of objects out here, as we'll get into a little later, that first gave astronomers a way to detect the cloud's existence at all. Long before anyone could see it directly, the objects that make up this vast, distant population are not rocky bodies like the asteroids that orbit between Mars and Jupiter. They are, almost without exception, icy. Frozen water, frozen methane, frozen ammonia, frozen carbon monoxide, locked together in solid, dark, faintly reflective bodies that range from small specks to objects tens of miles across. In a very real sense, these are leftover building materials. Most of what's out there formed at the very beginning of the solar system's history, something like 4.5 billion years ago, and has simply been sitting in the deep cold of space ever since, largely untouched. There's a common misconception worth clearing up early, because it shapes how people imagine this place. When you hear the word cloud, and you hear that it contains trillions of objects, it's natural to picture something dense, maybe even hazardous, a thick field of ice chunks that a spacecraft would need to carefully weave through. The reality is almost the opposite. Despite containing an enormous number of individual bodies, the volume of space involved is so staggeringly large that the average distance between any 2 neighboring objects is measured in the tens of millions of miles. If you somehow found yourself standing on one of these icy bodies, in the middle of the outer Oort Cloud, the sky around you would look almost entirely empty. You would not see any of the trillions of other objects sharing this region with you, no matter which direction you looked. You would not even recognize our sun as a sun in the way we know it on Earth. From that distance, it would simply be the brightest point of light in an otherwise ordinary star, indistinguishable at a glance from any other star. It would be a profoundly lonely, dark, and quiet place to stand. And for the ordinary objects that live there, that emptiness is simply their permanent condition. It's tempting to imagine this shell of ice as something that has simply always been there. A static ring of leftover material sitting quietly at the edge of the system since the very beginning, undisturbed and unchanging. The actual history is considerably more violent and considerably more interesting, because almost none of that material formed where it currently resides. The icy bodies that now drift through the Oort Cloud were mostly born much closer to the Sun, in the same general region where the giant planets themselves took shape. In the early history of the solar system, the orbits of Jupiter, Saturn, Uranus, and Neptune were not settled into the stable, nearly circular paths we observe today. According to the models astronomers currently favor, often grouped under the general idea of early giant planet migration, these massive worlds drifted substantially during the system's first several 100 million years, moving closer to the Sun in some phases and further away in others in a slow, gravitationally choreographed rearrangement. As these giant planets moved, their gravity acted like a repeated slingshot on the smaller icy bodies nearby. Jupiter and Saturn, and to a lesser extent Uranus and Neptune, plowed through the debris left over from planet formation and flung enormous numbers of icy planetesimals outward, away from the Sun on highly elongated orbits. Some of these objects were thrown with enough force to escape the Sun's gravity entirely, drifting off permanently into interstellar space, becoming what astronomers now call free-floating or rogue objects, unbound to any star. A large fraction of the ejected material, however, did not quite reach escape velocity. These bodies traveled outward until they reached the very outer limit of where the Sun's gravity could still, just barely, hold on to them, and there they slowed and effectively stalled, hanging at the edge of the Sun's gravitational reach, rather than escaping it completely. Over the following billions of years, gentle nudges from the combined gravity of the Milky Way galaxy and from other stars passing at a distance gradually reshaped the orbits of this stalled material, smoothing out their original planet-influenced paths into the broadly spherical distribution we associate with the outer Oort Cloud today, looked at this way. The Oort Cloud is less like a pristine deep freezer that has always held its contents in careful storage, and more like a kind of cosmic junkyard, filled with construction material that the outer planets swept up and threw away during a chaotic and comparatively brief early phase of the solar system's history, 4 billion years ago or more. It just so happens that the leftover material was flung far enough, and slowly enough, that gravity never quite let it go completely, and it has been drifting in that unstable balance ever since. This immense distance from the Sun creates a very particular physical situation for anything sitting out there. Here on Earth, the Sun's gravity is overwhelmingly dominant. It holds the planet in a tight, predictable, essentially permanent orbit, and nothing else in the galaxy meaningfully competes with that grip. Out in the Oort Cloud, the situation is far more delicate. The Sun's pull on objects at that distance is extremely weak. Weak enough that it is no longer the only significant gravitational influence acting on them. This is the point at which the solar system stops being an isolated bubble and starts genuinely interacting with the wider galaxy. Astronomers describe this influence using the term galactic tide, in much the same way that the Moon's gravity raises tides in Earth's oceans. The enormous combined mass of the Milky Way, including the dense disk of stars and gas that makes up most of the galaxy and the concentrated mass near the galactic center, exerts a gentle but persistent tidal pull on the outer Oort cloud. This force is constantly working against the Sun's already weak grip on that distant material. The galactic tide doesn't rip the Oort cloud apart, but it does shape it. It's thought to be one of the main reasons the outer Oort cloud maintains its broadly spherical form rather than settling down into a flat disk the way the planets have. The tension between the Sun's fading pull and the galaxy's steady tug keeps stretching and redistributing the cloud. And that ongoing tension appears to be part of what keeps the whole structure from collapsing into the same flattened shape as everything closer in. Because the Sun's hold on this material is so fragile, the outer Oort cloud is also unusually susceptible to outside interference, in a way that nothing closer to the Sun really is. It behaves less like a solid, sealed wall and more like a permeable membrane, open to influence from beyond the solar system. Other stars in the Milky Way are, of course, in constant motion, slowly drifting through the galaxy along their own paths, and every so often, one of them passes relatively close to our own solar system. When a star comes within a few light years of the Sun, its gravity is enough to noticeably disturb the outer Oort cloud, effectively giving the cage a shake. We know this isn't a purely hypothetical concern, because astronomers have identified a specific star on a specific collision course with our outer shell. The star in question, a small red dwarf called Gliese 710, currently sits about 60 light-years away from the Sun. By carefully tracking its position and motion, astronomers have calculated that in roughly 1 million years, it will pass directly through the outer regions of the Oort cloud, coming within about 13,000 astronomical units of the Sun at closest approach. That is not a distant, glancing encounter. It amounts to a direct pass through the outer shell of our own solar system. When it happens, the star's gravity is expected to scatter a substantial number of the icy bodies living out there, sending many of them off into deep interstellar space entirely, while nudging many others onto new orbits that dip inward toward the Sun and the planets. The result, over an extended period that could last for millions of years, is likely to be an elevated rate of comets entering the inner solar system. A slow-motion comet shower triggered by a single stellar flyby. Encounters like this are a useful reminder that the Oort cloud isn't simply a static, forgotten border sitting quietly at the edge of things. It's a dynamic, if extremely slow-moving environment, one that genuinely links the long-term fate of the inner solar system, including Earth, to the broader motion of stars across the galaxy. What happens near the Sun is not entirely a local story. There's an uncomfortable fact sitting underneath everything described so far. We have never actually seen the Oort cloud, despite decades of increasingly powerful telescopes. And despite genuinely extraordinary advances in space-based observation, no one has ever captured a confirmed image of an object sitting out there in that distant shell. No specific icy body has ever been tracked as it orbits at Oort cloud distances. Everything we believe about its structure, its size, and its contents rests on indirect reasoning rather than direct observation. That naturally raises an obvious question. If no one can see it, how can astronomers be so confident it exists at all, let alone describe its shape and scale in such detail? The honest answer starts with a problem of simple physics: lighting. Objects in the Oort cloud don't generate their own light. Like the planets, and like comets closer to home, they only shine by reflecting sunlight, but at a distance of tens of thousands of astronomical units. The Sun itself is reduced to little more than an ordinary, moderately bright star in the sky. and the amount of sunlight actually reaching an object out there is almost vanishingly small. Trying to spot a lump of ice a few miles across, illuminated by starlight-level sunshine from many light years worth of distance, is a bit like trying to spot a single dark stone lying against a black backdrop from 1,000 miles away. It's not merely difficult with current optical telescopes. It's effectively beyond their reach entirely. No matter how the technology has improved, a reasonable next thought might be that infrared telescopes, which detect heat rather than reflected visible light, could sidestep this problem. In practice, they run into their own version of the same wall. Objects in the Oort Cloud are not just extremely dark, they are also extremely cold, sitting only a few degrees above absolute zero, the theoretical coldest possible temperature. At those temperatures, an object emits almost no infrared radiation of its own, and whatever faint heat signature it does produce is nearly indistinguishable from the general background temperature of deep space itself. Combine that with the object's small size and the immense distance involved, and even the most sensitive infrared instruments currently available simply cannot separate a genuine signal from the surrounding noise. In short, it isn't one single obstacle keeping the Oort Cloud hidden from direct view. It's several compounding problems at once: extreme darkness, extreme cold, small size, and extreme distance, all working together against us. So instead of direct observation, the existence of the Oort Cloud rests on a different kind of evidence entirely. One built from mathematics and the careful study of comets that do, eventually, wander close enough to see. The story of that reasoning goes back to the middle of the 20th century, though its roots reach further back still, into a much older puzzle involving two very different-looking families of comets. Comets that we can readily observe fall into two broad categories, distinguished mainly by how long they take to complete one orbit around the Sun. The first category, short-period comets, complete an orbit in under 200 years. Halley's Comet is probably the most famous example, and these comets tend to travel on orbits fairly close to the same flat plane the planets occupy. Their origin point, astronomers have determined, is a somewhat closer region of icy debris just beyond Neptune's orbit, called the Kuiper Belt, a structure we can actually observe directly. In a way, the Oort Cloud cannot yet be observed. The second category is stranger. Long-period comets take anywhere from a few hundred to many hundreds of thousands of years to complete a single orbit. Comet Hale-Bopp, visible from Earth in the late 1990s, will not return to the inner solar system for roughly another 2,000 years. Comet West, observed decades earlier, follows an orbit lasting on the order of 250,000 years. Traveling on orbits that long and that large requires reaching distances far beyond anything the Kuiper Belt could plausibly supply. The key clue that eventually led astronomers to the Oort Cloud came not from where these long-period comets went, but from the angles at which they arrived. Around 1950, the Dutch astronomer Jan Oort, building on earlier ideas, examined the orbital paths of a substantial sample of long-period comets and noticed something the short-period population simply didn't show. Rather than approaching from the same flat, planet-like plane, these comets arrived from every conceivable direction, dropping down from high above the Sun's North Pole, rising up from below its South Pole, and everything in between, with no preference for any particular orientation at all. That randomness turned out to be the crucial piece of the puzzle. If these comets originated from a flat, ring-shaped reservoir, similar in geometry to the Kuiper belt or the asteroid belt. They would all tend to arrive along roughly the same plane, the way the short-period comets do. The fact that they instead arrived uniformly from every direction implied that whatever reservoir was feeding them had to surround the sun uniformly as well. It had to be, in other words, a sphere, not a ring. There was a second, independent line of reasoning pointing toward the same conclusion, this one having to do with simple supply and demand. Comets are fragile objects. Every time one passes close to the sun, solar heating boils away some of its surface ice, producing the glowing tail that makes comets so visually striking, and gradually eroding the comet's material with each pass. After enough close approaches, a comet eventually disintegrates entirely or simply runs out of ice to lose. Given that the solar system is roughly 4.5 billion years old, any comets present at the very beginning should, by simple attrition, have burned out long, long ago, and yet we continue to observe new long-period comets making their first recorded approach to the inner solar system, seemingly fresh, seemingly untouched by prior passages. For that observation to make sense, there has to be some ongoing supply, some deep reservoir holding a vast number of comets in reserve, occasionally releasing a fresh one to replace the ones lost to solar heating over the eons. That reservoir sitting far out in the cold dark, patiently waiting for a gentle gravitational nudge from a passing star to send one of its members falling inward, is what we now call the Oort Cloud. The broader concept of a distant cometary reservoir predates Oort's specific calculations by a couple of decades. An Estonian astronomer named Ernst Kippik first proposed, in 1932, that such a reservoir of comets might exist at the outer edge of the solar system, based on more general reasoning about comet dynamics. It was Jan Oort, roughly 2 decades later, who independently developed the idea further and gave it the rigorous, mathematical footing that eventually made it convincing to the wider astronomical community. Oort demonstrated that the observed uniform, random direction distribution of long-period comet orbits required a spherical source, and that mathematical treatment is what ultimately gave the structure its name, even though Kapik's earlier, more preliminary work is often acknowledged alongside it. It's worth pausing on how strange this is as a piece of scientific reasoning. Nobody photographed the Oort cloud, tracked a body within it, or sent a probe to survey its contents. Its existence was inferred entirely from the statistical behavior of a relative handful of comets, whose orbital angles simply didn't make sense unless a vast, roughly spherical reservoir was sitting out there, feeding them into the inner solar system on an ongoing basis. It remains, to this day, one of the more elegant examples of detecting something enormous and entirely invisible purely through the footprints it leaves behind. It's worth spending a little more time on the region that sits between the familiar planets and the Oort cloud proper, because it's easy to blur it together with the more distant shell. And the two are genuinely different places with genuinely different histories. The Kuiper belt, the source of most short-period comets, begins just past the orbit of Neptune, around 30 astronomical units from the Sun, and extends out to roughly 50 astronomical units. Unlike the Oort cloud, it is flat, occupying much the same plane as the planets, and it is close enough, and its members are large enough, that we can actually observe individual objects within it using ordinary telescopes. Pluto, reclassified in 2006 as a dwarf planet rather than a full planet, is by far the most famous resident of the Kuiper belt, but it's far from alone out there. Eris, a dwarf planet of comparable size, orbits in a similar region on a notably tilted and elongated path. New Horizons, the NASA spacecraft that gave humanity its first close look at Pluto in 2015, went on to fly past a second, much smaller Kuiper Belt object called Arrokoth in early 2019, providing the most detailed images we have ever obtained of a pristine, unaltered building block from the solar system's early history. Beyond the main body of the Kuiper Belt lies a stranger, sparser population, sometimes called detached objects or extreme trans-Neptunian objects, whose orbits stretch out far beyond what the belt's general structure would predict. The most famous of these is a body called Sedna, discovered in 2003, whose highly elongated orbit carries it from around 76 astronomical units at its closest, approach to the Sun out to more than 900 astronomical units at its most distant point, an orbit so extreme that a single lap takes over 11,000 years to complete. Objects like Sedna occupy an interesting middle ground. Dynamically speaking, they orbit too close at their nearest approach to be considered true Oort Cloud members, yet their farthest excursions carry them well past the outer Kuiper Belt and into the general territories some astronomers now describe as the inner Oort Cloud, or the Hills Cloud mentioned earlier. Several other bodies with similarly inclined orbits have been found in the years since Sedna's discovery, and their peculiar, tightly clustered orbital properties have led some researchers to propose that an as yet undiscovered massive planet, informally nicknamed Planet 9, might be lurking in the outer solar system, its gravity subtly shepherding this small population of distant objects into their unusual, aligned configuration. It's important to be honest about where that particular idea currently stands. The hypothesis remains actively debated within the astronomical community. Some researchers find the orbital clustering compelling enough to justify continued searching, while others argue that the effect may be explained by observational bias, since surveys tend to more easily detect objects in certain regions of the sky, or by other, less exotic gravitational influences. No such planet has been directly detected, despite years of dedicated searching using large ground-based telescopes and newer, more comprehensive sky surveys currently underway may either turn up convincing evidence for it or rule the idea out within the coming years. For now, it remains one leading hypothesis among several, rather than a settled fact. What's clear, regardless of how the Planet 9 question eventually resolves, is that the outer solar system is considerably more layered and more populated than the simple picture of planets, then Kuiper Belt, then empty space, then Oort Cloud might suggest. There appear to be multiple, overlapping populations of icy bodies out there, shaped by different formative processes and different gravitational histories, gradually blending from the flattened, close-in Kuiper Belt through the intermediate, extended orbits of objects like into the thick, disc-shaped inner Oort Cloud, and finally out into the broad, spherical outer Oort Cloud that defines the true edge of the Sun's domain. No discussion of the outer solar system feels complete without spending some real time with Voyager 1. Probably the single most famous piece of hardware humanity has ever sent outward, and a spacecraft whose story is tangled up with some genuinely persistent misconceptions about where exactly the solar system actually ends. Voyager 1 and its twin, Voyager 2, launched from Earth in originally designed for a multi-year tour of the outer planets. Voyager 1 flew past Jupiter in 1979 and past Saturn in 1980, capturing extraordinary imagery of both systems. including detailed views of Jupiter's moons and Saturn's rings that reshaped scientific understanding of the outer solar system at the time. Once its main planetary encounters were complete, mission planners set it on a trajectory that would carry it up and out of the solar system's flattened plane, heading generally outward, away from the Sun, on a path that continues to this day. Both Voyager probes carry an infamous golden record, a gold-plated copper disc containing recordings of music, natural sounds, spoken greetings in dozens of languages, and images intended to represent Earth and its inhabitants, included in case either spacecraft is ever recovered by some future civilization, human or otherwise. It remains one of the more poetic gestures in the history of space exploration, a kind of message in a bottle cast into the largest ocean imaginable. In 2012, headlines around the world declared that Voyager 1 had finally left the solar system, becoming the first human-made object to reach interstellar space. That announcement was technically accurate, according to one specific definition of the solar system's boundary, but it created a somewhat misleading impression of how much distance the spacecraft had actually covered relative to the system's true outer edge. Understanding why requires separating two very different boundaries that both get casually referred to using the phrase edge of the solar system. The first boundary is magnetic, not gravitational. The Sun constantly emits a stream of charged particles called the solar wind, blowing outward in every direction. This outward flow inflates a vast bubble around the entire solar system, a region where the Sun's magnetic field and its outward blowing wind dominate over the material and radiation of the wider galaxy. This bubble is called the heliosphere, and it extends roughly 100 to 120 astronomical units from the Sun, though its exact shape and size fluctuate somewhat with the Sun's own activity cycles. The outer edge of that bubble, the boundary where the outward pressure of the solar wind is finally overwhelmed by the pressure of the interstellar material beyond, is called the heliopause. Crossing the heliopause means leaving behind the region dominated by the Sun's magnetic influence, not leaving behind the region dominated by the Sun's gravity. Those are two entirely separate kinds of boundary, and it's easy, understandably, to conflate them. In 2012, Voyager 1 crossed the heliopause, registering a sharp drop in the density of solar-originated particles and a corresponding spike in cosmic rays arriving from beyond the solar system. The telltale signature scientists had been watching for. That was the moment, by the magnetic definition, that Voyager 1 entered interstellar space. But interstellar space, in this specific sense, is not remotely the same thing as leaving the solar system in the gravitational sense that actually defines its true outer boundary. The solar system, understood gravitationally, ends only where the Sun's gravity can no longer meaningfully hold onto anything at all. And by that measure, Voyager 1 had, at the moment of that famous announcement, barely cleared the front porch. As of the most recent tracking data, Voyager 1 sits at a distance of roughly 160 astronomical units from the Sun, traveling outward at a speed of about 38,000 miles per hour, or roughly 17 kilometers every second. That is an extraordinary speed by any everyday human standard, fast enough to cross a distance equivalent to the diameter of Earth in under 12 minutes. And yet, set against the true scale of the Oort Cloud, that speed effectively renders the spacecraft almost motionless. Voyager 1 currently sits in the mostly empty gap of space between the heliopause it crossed in 2012 and the inner edge of the Oort Cloud, still thousands of astronomical units away. At its current speed, the spacecraft will not reach even the very beginning of the Oort Cloud for several more centuries, with current estimates placing that milestone sometime around the year 2300, give or take, depending on exactly where the cloud's inner boundary is eventually determined to lie. There's a genuinely bittersweet element to this timeline, because Voyager 1 will not be operational by the time it gets there, or anywhere close to it. The spacecraft runs on a power source called a radioisotope thermoelectric generator, which converts the steady heat given off by decaying plutonium into usable electricity. That decay process is entirely predictable, and the power output has been steadily declining ever since launch. NASA engineers currently expect to have shut down the last of the spacecraft's remaining scientific instruments by around the year 2030, at which point Voyager 1 will fall permanently silent, transformed instantly from an active scientific mission into a piece of drifting, inert metal. That silent journey will continue for a very long time. Even after its instruments go dark, Voyager 1 will keep moving outward at essentially the same speed, and current estimates suggest it will take something on the order of 30,000 years for the spacecraft to fully pass through the Oort Cloud and finally emerge on the far side. Only at that point, tens of thousands of years from now, will it have genuinely left the solar system by the gravitational definition that actually matters most. There's something worth sitting with in that number. Recorded human history, from the earliest known writing systems to the present day, spans something on the order of 5,000 or 6,000 years. The journey Voyager 1 still has ahead of it, just to clear our own solar system's true outer boundary, is roughly 5 or 6 times longer than that entire stretch of recorded history. We built a machine capable of traveling for decades at tens of thousands of miles per hour, faster than almost anything else humanity has ever launched, and even so, it will take a span of time longer than civilization itself has existed just to cross the threshold of our own backyard. It's worth being clear about what kind of barrier that Oort Cloud actually presents, because it's easy to imagine it as a physical wall, something a spacecraft would have to carefully navigate through, dodging chunks of ice the way a ship might weave between icebergs. That image, as covered earlier, isn't accurate. If a spacecraft were piloted outward through the Oort Cloud, it would not encounter a dense field of debris requiring careful steering. The danger of the Oort Cloud isn't found in what is out there. It's found in what is not. The barrier, in other words, is the emptiness itself. And that emptiness creates a genuinely severe engineering problem for any realistic vision of interstellar travel. In science fiction, spacecraft often make use of a strategy sometimes called island hopping, stopping periodically at convenient asteroids, moons, or other bodies to mine water ice and convert it into usable propellant, allowing a vessel to travel enormous distances without needing to carry an impossibly large fuel supply from the very start of the journey. Within the inner solar system, this idea isn't purely fictional. A spacecraft really could, in principle, travel from Earth to Mars, then onward to the asteroid belt, then to the icy moons of Jupiter or Saturn, refueling at each stop along the way, because the various islands involved are, relatively speaking, close together once a spacecraft crosses the orbit of Neptune. However, the islands effectively disappear. The Oort Cloud may contain trillions of individual objects, but they are spread across a volume of space so enormous that their overall density is, for practical purposes, close to zero. The average distance between any two icy bodies out there is comparable to the distance between Earth and Saturn, a gap that would take conventional spacecraft years to cross, even at high speed. Island hopping, in any meaningful sense, simply is not possible out there. There are no convenient refueling stops. A spacecraft entering that region is entering something closer to a genuine desert, one that happens to be tens of thousands of astronomical units wide. This absence of any resupply option runs headlong into a piece of basic physics known as the rocket equation. First worked out in a rigorous form by the Russian scientist Konstantin Tsiolkovsky at the end of the 19th century, the rocket equation describes a frustrating exponential relationship between a spacecraft's final speed, the efficiency of its engines, and the amount of fuel it must carry, because there are no pit stops available anywhere within the Oort Cloud. Any spacecraft attempting to cross it would need to carry every last unit of propellant it will ever use for the entire journey, from the very moment it departs Earth. The trouble is that fuel itself has mass. An additional mass requires additional fuel just to move it, which in turn adds still more mass, in a spiraling relationship that grows exponentially rather than in a simple, linear way. This effect makes it, with anything resembling current chemical rocket technology, essentially impossible to build a spacecraft capable of crossing the Oort Cloud and reaching genuine interstellar space beyond it within any reasonable span of time. With today's propulsion systems, the Oort Cloud functions as an effectively impassable barrier for any realistic human mission. To put a number on just how impassable, a hypothetical spacecraft launched today using current chemical propulsion, attempting to cross the full width of the Oort Cloud, would likely require somewhere on the order of 30,000 years to complete the trip. The same time scale, coincidentally, that Voyager 1 itself will eventually take. A journey of that length isn't really a journey in any conventional sense. It's closer to a geological event, a span of time comparable to entire ice ages or the rise and fall of numerous past civilizations. Any human crew launched on such a mission today would almost certainly see their entire launching civilization change beyond recognition, or cease to exist altogether, long before the ship reached its destination. The crew itself would need to live, reproduce, and die across hundreds of generations, entirely within the dark, empty void between the stars. A scenario often explored in fiction under the heading of generation ships, but one that remains, for now, firmly outside the reach of actual engineering. Some more speculative proposals have attempted to sidestep the worst of the rocket equation's constraints. Concepts like nuclear pulse propulsion, which would use a sequence of small nuclear detonations behind the spacecraft to generate thrust, or more exotic ideas involving fusion-based drives, antimatter engines, or laser-driven light sails such as those explored by the privately funded Breakthrough Starshot initiative, all attempt to achieve dramatically higher exhaust speeds or entirely different propulsion mechanisms that could, in principle, cut travel times down from tens of thousands of years to a few decades or centuries for extremely small, lightweight probes. None of these approaches has yet been demonstrated at anything close to the scale needed for a genuine interstellar crossing, and each carries its own severe unresolved engineering challenges, but they do represent active, ongoing lines of serious research rather than purely fictional speculation. Taken together, this combination of gravitational scale and the sheer emptiness in between means the Oort Cloud functions as a kind of natural quarantine, separating our solar system from the rest of the galaxy far more effectively than any physical structure ever could. For the foreseeable future, at least, humanity remains what might be called an island species, cut off from easy contact with the rest of the galaxy, not merely by distance, but by the underlying physics of what it actually takes to move a spacecraft, and any crew it might carry across that distance. We can send robotic ambassadors outward into the dark, as we already have with the Voyager probes and others. But our physical reach as a species remains, for now, bounded by the vast shell surrounding us. It would be a mistake to think of our own Oort Cloud as a strange, singular feature unique to our particular solar system. The general picture emerging from decades of observation of other star systems suggests that structures like this are probably a fairly ordinary byproduct of planet formation, and that many, perhaps most, stars with planetary systems of their own end, up surrounded by something broadly similar. The evidence for this comes largely from what astronomers call debris disks, rings or shells of dust and icy material observed around numerous other nearby stars, often detected through the faint infrared glow given off as starlight warms that material just enough to radiate weakly. Stars such as Vega, Fomalhaut, and Beta Pictoris, among many others, all show clear evidence of substantial debris structures surrounding them, thought to represent the same kind of leftover planet-forming material that, in our own system, was scattered outward by the migrating giant planets to eventually form the Oort Cloud. Some of these systems show debris arranged in comparatively narrow rings, similar in spirit to our own Kuiper belt, while others show broader, more extended structures that may correspond to something more like an outer, Oort Cloud-style shell, though at these distances and with current instruments, the details remain difficult to pin down precisely. Perhaps the most direct evidence that other stars really do eject material outward, in a manner comparable to what happened in our own early solar system, comes from a genuinely new category of astronomical object, interstellar visitors, objects that formed around other stars entirely, and have since drifted, mostly at low relative speeds, into and eventually back out of our own solar system. The first confirmed example, an elongated, unusually shaped body named Oumuamua, was detected passing through the inner solar system in 2017, moving on a trajectory that made clear it did not originate anywhere within our own system, and was simply passing through on its way back out into interstellar space. A second confirmed interstellar object, a genuine comet given the name to I/Borisov, following the standard naming convention for interstellar objects, was detected in 2019, and unlike it displayed the classic glowing tail and outgassing behavior typical of an ordinary comet, strongly suggesting it originated as icy material ejected from some other star's own planet-forming disk, quite plausibly from that other star's equivalent of an Oort cloud, sent drifting between the stars by the same kind of gravitational ejection process that scattered material outward. During our own solar system's early, chaotic phase, the existence of these interstellar wanderers strongly supports the broader picture that Oort cloud-like structures and the occasional ejection of material from them into interstellar space are likely common throughout the galaxy, a natural consequence of how planetary systems form and settle over time. Current models estimate that the Milky Way as a whole may contain a genuinely enormous population of these free-floating interstellar objects, drifting silently between the stars, the collective, scattered debris of countless other planetary systems' own early histories, largely invisible to us, except on the rare occasions when one happens to drift close enough to be detected passing through our own neighborhood. This broader context occasionally intersects with a more speculative and more contested area of science. The question of whether material exchanged between star systems in this way, icy bodies potentially carrying basic organic compounds, or even, in principle, hardy microbial life, could play any role in spreading the basic chemical building blocks of life, or conceivably life itself, from one star system to another. This idea, generally known as panspermia, and specifically the interstellar version of it, sometimes called lithopanspermia, remains a minority position within the scientific community, and it faces serious, largely unresolved challenges, particularly around whether anything biological could plausibly survive the enormous timescales, extreme cold, and intense radiation exposure involved in an interstellar crossing. It is, at this stage, one hypothesis among several regarding the origins and spread of life, worth mentioning honestly as part of the broader picture, but genuinely far from settled, and it should not be mistaken for an established or widely accepted explanation. Comets themselves are worth lingering on a little longer, since they are, in a sense, our only real messengers from this distant region. Small samples of ancient material that occasionally make the long journey inward and become, briefly, visible and studyable. For most of human history, comets were viewed with a mixture of fascination and dread, often interpreted as omens, warnings of disaster, or signs of coming upheaval, appearing in the historical record around major events from the death of rulers to the outcomes of battles, simply because they were unpredictable, dramatic, and rare enough to feel significant whenever they happened to appear. The shift toward understanding comets as natural, physical objects following ordinary laws of gravity, rather than supernatural omens, owes a great deal to the English astronomer Edmund Halley, working in the late 17th and early 18th centuries, using the newly developed gravitational framework laid out by Isaac Newton. Halley examined historical records of past comet sightings and realized that several apparently separate comets, observed roughly 76 years apart across multiple centuries, were very likely the same object, returning again and again on a long, predictable, elliptical orbit. He successfully predicted its return in 1758, a date he did not live to see himself, having died some years earlier, and the comet was subsequently named in his honor. Halley's comet remains, to this day, the most famous and most easily recognized short-period comet, and its confirmed periodic return marked one of the earliest and most convincing demonstrations that Newton's laws of gravity applied not just to the planets, but to smaller, more erratic bodies as well. Since Halley's time, our understanding of comet composition and behavior has deepened enormously, helped along in the more recent past by a series of dedicated spacecraft missions sent specifically to study these objects up close. The European Space Agency's Giotto probe flew directly past Halley's comet during its 1986 return, providing the first close-up images of a comet's icy, irregularly shaped nucleus. NASA's Deep Impact mission, launched in 2005, deliberately released an impactor designed to collide with Comet Tempel 1, allowing scientists to study the material excavated from beneath the comet's surface. The Stardust mission successfully collected and returned actual particles from the tail of Comet Wild 2, delivering physical samples of cometary material back to laboratories on Earth for the first time, and the European Space Agency's Rosetta mission, arriving at Comet 67P, known informally as Comet Churyumov, in 2014, went further still, entering orbit around the comet's nucleus and deploying a small lander named Philae onto its surface, providing an unprecedented, extended, close-up study of a single comet's structure, composition, and behavior as it approached the Sun and became increasingly active. These missions have collectively confirmed what indirect evidence had long suggested, that comets are essentially loosely bound mixtures of ice and dust, sometimes described informally as dirty snowballs, preserving material that has remained largely unaltered since the very earliest stages of the solar system's formation. Studying that preserved material offers a genuinely unique window into the chemical conditions present at the birth of the solar system, conditions that have been almost entirely erased from the planets themselves through billions of years of geological activity, but which remain frozen, quite literally, within cometary ice. There's also a more dramatic, occasionally violent side to cometary behavior worth mentioning: sun-grazing comets, a specific population that follows orbits carrying them extremely close to the Sun's surface at their nearest approach, sometimes passing within a few solar radians. Many of these belong to a related family known as the Kreutz group, thought to be fragments of a single, much larger comet that broke apart at some point in the past, likely due to the Sun's own gravitational tidal forces during a previous close approach. Some sun-grazing comets survive their close encounters, considerably diminished, while others disintegrate entirely, torn apart by heat and gravity in full view of solar observatories that continuously monitor the region immediately surrounding the Sun. Some researchers have gone further than simply describing the Oort Cloud as a passive reservoir, and have asked whether periodic disturbances out there might have left a detectable mark on the history of life on Earth itself. Starting in the 1980s, several paleontologists and astronomers noticed what appeared to be a rough periodicity in the timing of mass extinction events preserved in the fossil record, with major extinctions seeming to cluster at intervals of roughly 26 to 30 million years. This observation led to a striking, if ultimately speculative, hypothesis, sometimes referred to as the Nemesis hypothesis, proposing that the Sun might have an unseen, extremely distant companion star, a faint red or brown dwarf on a very long, elongated orbit that periodically swings close enough to disturb the Oort cloud, triggering elevated comet impact rates on Earth on a roughly matching timescale. Despite considerable searching, no such companion star has ever been detected, and later, more careful statistical analysis of the fossil record has cast serious doubt on whether the original periodicity was ever as robust as initially claimed, with some researchers arguing it may be largely an artifact of incomplete or unevenly sampled geological data rather than a genuine underlying pattern. The Nemesis hypothesis is generally regarded today as an interesting historical idea that did not hold up well under further scrutiny. Rather than an accepted explanation for extinction patterns, though the broader, less specific idea that passing stars occasionally disturb the Oort cloud and modestly raise comet impact rates over long timescales, as with the confirmed future case of Gliese 710, remains entirely uncontroversial and well supported. It's worth stepping back briefly to consider the environment the Sun itself was born into, since that context shapes how astronomers think about the earliest history of the Oort cloud's formation. Stars, including the Sun, are generally understood to have formed not in isolation, but within large, temporary clusters containing hundreds or even thousands of sibling stars, all condensing together out of the same enormous collapsing cloud of gas and dust. Over time, gravitational interactions within the cluster, combined with the broader rotation of the galaxy, gradually scattered these sibling stars apart, spreading them out across the galaxy until, billions of years later, they bear little obvious resemblance to a once tightly bound family. It's thought that during this early, more crowded phase of the Sun's history, close stellar encounters would have been considerably more frequent than they are today, potentially playing a significant role in shaping the earliest stages of the outer Oort Cloud, before the Sun eventually drifted away from its birth cluster into the comparatively isolated position it now occupies. Locating any of the Sun's actual sibling stars today, among the roughly 100 billion or more other stars in the Milky Way, has proven extraordinarily difficult, though a small number of candidate stars, identified through detailed chemical composition matching, have occasionally been proposed, returning briefly to the heliosphere and its surrounding boundary regions. There's a bit more nuance worth adding to the picture. The heliosphere is not a perfectly smooth, symmetrical bubble. As the Sun moves through the galaxy, it drags the heliosphere along behind it, somewhat like the way a boat's wake trails out behind it as it moves through water, creating a longer, more extended tail on the side facing away from the Sun's direction of travel, and a more compressed, blunter shape on the leading side. Voyager 2, the twin spacecraft to Voyager 1, took a different trajectory after its own planetary flybys, and crossed the heliopause on its own path in 2018, 6 years after Voyager 1, providing scientists with a valuable second data point on the shape and thickness of this boundary region from an entirely different direction and location. There was, for some years, active debate over whether the heliosphere possesses a genuine bow shock, an abrupt, turbulent boundary analogous to the shock wave that forms in front of a supersonic aircraft, where the solar wind first begins to interact violently with the surrounding interstellar medium. More recent analysis, incorporating updated measurements of the actual speed and direction of the interstellar medium relative to the Sun, has suggested that the heliosphere most likely does not move fast enough relative to its surroundings to produce a true shockwave in the strict physical sense, and instead produces a gentler, more gradual disturbance, sometimes called a bow wave. This remains an area of active refinement, as researchers continue incorporating new data from both Voyager spacecraft and various other missions designed to study the boundary regions of the solar system, even without any hope of directly observing the individual Oort Cloud objects in the near future. Several ongoing and upcoming projects are expected to meaningfully sharpen our understanding of this distant region over the coming decade or two. The Vera C. Rubin Observatory, a large ground-based telescope in Chile that recently began its extended, multi-year survey of the entire visible sky, is expected to dramatically increase the number of known long-period comets and other distant solar system objects, simply by repeatedly imaging the whole sky with far greater sensitivity than previous surveys managed. Every new long-period comet discovered adds another data point to the statistical picture Oort himself first began building nearly a century ago, gradually refining estimates of the cloud's total population, its inner and outer boundaries, and the finer details of its overall shape. The James Webb Space Telescope, since becoming operational in the early 2020s, has also contributed indirectly to this picture, primarily through its extraordinarily sensitive infrared observations of debris disks surrounding other nearby stars, offering increasingly detailed comparisons between our own solar system's outer structure and those forming, or already formed, around other stars at various stages of their development. These comparisons help place our own Oort Cloud in a broader evolutionary context, clarifying which of its features are likely typical outcomes of planet formation in general, and which might be more particular to our own solar system's specific history. There has also been serious, if still largely conceptual, discussion within the space science community about a dedicated mission sometimes referred to as an interstellar probe, a spacecraft explicitly designed from the outset to travel far beyond where either Voyager was ever intended to go, ideally carrying a more capable and longer-lasting suite of instruments, specifically tailored to studying the heliosphere's outer boundary and, eventually, the inner edge of the Oort Cloud itself. Such a mission remains in early planning and feasibility study stages without a confirmed launch date, and would still face the same fundamental propulsion limitations discussed earlier, meaning even an optimally designed spacecraft using current or near-future technology would likely still take many decades simply to reach the outer heliosphere, let alone the Oort Cloud's true inner boundary. Even so, a mission specifically built for that kind of extended journey, rather than one repurposed after completing an entirely different primary mission as both Voyager probes were, could substantially improve the quality of data gathered from that region over the coming half-century or so. New Horizons, the spacecraft responsible for the historic 2015 flyby of Pluto and the subsequent 2019 flyby of the more distant Kuiper Belt object Arrokoth, remains active today in an extended mission phase, continuing to study the outer solar system structure and searching for additional distant objects it might be able to observe, or potentially even fly past, as it continues its own outward journey, though it operates at a considerably slower speed than either Voyager and will likewise never come close to reaching actual Oort Cloud distances within its operational lifetime. Despite all of this ongoing and planned work, honest uncertainty remains at the very core of our current understanding of the Oort Cloud. Estimates of the total number of objects it contains vary considerably depending on the particular model used, though figures in the range of several trillion icy bodies, larger than roughly half a mile across, are commonly cited. Estimates of its total combined mass are similarly uncertain, generally placed at somewhere between a few times and perhaps 10 or more times the mass of Earth, though this figure remains one of the least tightly constrained numbers in solar system science, precisely because it rests on statistical modeling of comet orbits rather than any kind of direct census. The precise location of both its inner and outer boundaries likewise remains an active subject of ongoing refinement, rather than a fixed, universally agreed upon number, and different research groups, using different modeling assumptions, continue to arrive at somewhat different figures for both. It's worth returning briefly to the giant planet migration story described earlier, because the specific mechanics involved are more intricate and more interesting than a simple picture of planets drifting slowly outward and inward suggests. The model most widely favored today, often called the NICE model, after the French city where it was first developed in detail, proposes that Jupiter and Saturn, early in the solar system's history, gradually migrated toward each other until their orbital periods fell into a particular mathematical relationship, known as a resonance. In this specific case, a 2-to-1 resonance, meaning Jupiter completed almost exactly 2 orbits for every 1 orbit Saturn completed. Crossing that resonance point triggered a period of considerably more dramatic orbital instability. Throughout the outer solar system, Uranus and Neptune, previously on more modest, closely spaced orbits, were flung outward, sometimes even swapping their relative positions in the process. while a substantial portion of the icy debris disk that had originally surrounded all 4 giant planets was violently scattered in every direction. Some inward toward the Sun, some outward toward interstellar space, and a significant remaining fraction outward into the stalled, unstable orbits that eventually settled into the Oort Cloud as gravity and the passage of billions of years gradually smoothed out their initial chaotic paths. This period of instability is thought to have occurred a few 100 million years after the solar system's initial formation, and some researchers have connected it to a spike in impact. Craters observed on the Moon and inferred elsewhere in the inner solar system, an episode sometimes referred to as the Late Heavy Bombardment, though the precise timing, severity, and even the basic reality of that particular bombardment spike remains an area of ongoing debate among planetary scientists, with more recent studies raising questions about whether the crater record actually supports a single, sharply defined bombardment event or a more gradual, extended decline in impact rates instead, regardless of the exact details still being worked out. The broader picture that a chaotic, comparatively brief period of gravitational rearrangement among the outer planets is what ultimately scattered enough icy material to build both the Oort Cloud and much of the Kuiper Belt, remains a central pillar of current solar system formation theory, supported by an increasing number of independent lines of evidence beyond the original crater counting arguments, including detailed computer simulations that successfully reproduce many of the outer solar system's present-day orbital characteristics when run forward from plausible early starting conditions within the Kuiper Belt itself. Astronomers have identified 2 broadly distinct populations that likely trace back to different chapters of this same turbulent history. The so-called cold classical objects follow orbits that are close to circular and only mildly tilted relative to the plane of the planets, suggesting they may have formed largely in place, relatively undisturbed by the giant planet's migration. The so-called hot classical population, by contrast, follows more elongated, more steeply tilted orbits, generally interpreted as evidence that these objects were originally scattered from other locations entirely, likely closer to the Sun, and only ended up in their current positions as an indirect consequence of the same migration event that eventually populated the Oort Cloud. Studying the different orbital and even compositional characteristics of these 2 populations offers another independent way of testing and refining the broader migration story. Beyond the comet orbit statistics, Oort originally relied on, the broader galaxy that surrounds our solar system deserves a little more attention too, since the Oort Cloud's very existence and its eventual fate is tied so closely to the wider structure the Sun happens to be moving through. The Milky Way is a barred spiral galaxy containing somewhere in the range of 100 to 400 billion stars, arranged into a flattened disk with several sweeping spiral arms, a dense, bright central bulge, and an enormous, roughly spherical halo of older stars, gas, and dark matter surrounding the whole structure. The Sun sits well out from the galactic center, roughly 26,000 light-years away, orbiting the center of the galaxy once every 222–230 million years or so, a span of time sometimes informally called a galactic year. As the Sun makes its slow circuit around the galaxy, it doesn't travel in a perfectly flat, simple circle confined to the galaxy's central plane. It also oscillates gently up and down through that plane, moving above it, then back down through it, then below it, and back up again in a slow, repeating cycle that takes something on the order of 30 to 70 million years to complete, depending on which particular model of the galaxy's mass distribution is used. Some researchers have speculated, though again with considerable uncertainty, that these periodic crossings through the denser central plane of the galaxy might correspond to variations in the strength of the galactic tide acting on the Oort Cloud, since the density of surrounding material, and therefore the tidal force involved, would naturally be somewhat higher near the plane than well above or below it. If real, this effect could translate into a very slow, very subtle, periodic variation in the rate of comets nudged inward toward the Sun over these tens of millions of years timescales. Though, much like the earlier Nemesis hypothesis, this remains a speculative refinement built on top of a much more solidly established underlying phenomenon, the galactic tide itself, rather than a confirmed, independently verified effect in its own right. It's genuinely remarkable, when you sit with it for a moment, that the fate of a small icy body drifting through the outer reaches of our solar system is connected, even if only weakly and indirectly, to the Sun's slow orbit around the center of an entire galaxy, and to that galaxy's own broader structure and mass distribution. The Oort Cloud sits, in a very real sense, at the boundary between two very different scales of astronomy: the relatively intimate, well-mapped scale of our own solar system, and the vastly larger, far less intimately understood scale of the galaxy the solar system happens to call home. It's one of the few places where those two scales meaningfully overlap and interact. The giant planet migration described earlier didn't just scatter material out to the stalled, elliptical orbits that eventually became the Oort Cloud. A meaningful fraction of the debris, as mentioned briefly before, was ejected with enough energy to escape the Sun's gravity altogether, becoming permanently unbound. Free-floating objects drifting through interstellar space with no host star at all. For a long time, this was purely theoretical, an expected but unconfirmed byproduct of planet formation models. Over the past couple of decades, observational astronomy has begun to catch up with that prediction in a genuinely striking way, using a technique called gravitational microlens, in which the gravity of a passing object briefly bends and magnifies the light of a more distant background star. Astronomers have detected a growing number of candidate free-floating planets, objects with masses comparable to Jupiter, or in some cases even smaller, seemingly unattached to any star, drifting alone through the galaxy. Current estimates, still carrying substantial uncertainty, suggest that free-floating planets of this kind might actually outnumber the stars in the Milky Way, a genuinely startling possibility if it holds up under further scrutiny, implying that planet formation routinely produces far more objects than any given planetary system ultimately manages to hold onto. If that picture is broadly correct, then the same violent, chaotic process of planetary migration that carved out our own Oort Cloud and flung a portion of our system's icy debris into permanent interstellar exile has likely played out, with variations, around a very large number of other stars throughout the galaxy's history. The free-floating objects wandering the galaxy today, along with the interstellar visitors like Oumuamua and Borisov mentioned earlier, may collectively represent the accumulated debris of that process, replayed billions of times over across the Milky Way's long history, a quiet reminder that planet formation is, in some sense, always at least a little bit wasteful, always scattering more material outward than any resulting planetary system ultimately keeps for itself. There's a related and genuinely fascinating chemical story tied up in all of this scattered, icy debris. one that connects directly back to the question of where the basic ingredients for life originally came from. When the European Space Agency's Rosetta mission studied Comet 67P up close, its instruments detected the amino acid glycine in the material surrounding the comet's nucleus, along with phosphorus and a range of other simple organic molecules. The first confirmed detection of an amino acid associated with a comet. Amino acids are the basic building blocks that combine to form proteins, one of the essential classes of molecules required for life as we understand it, and finding one preserved within cometary material offered fairly direct evidence that at least some of the chemical raw materials relevant to biology were already present in the early solar system's icy debris, long before life ever appeared on Earth. This doesn't, on its own, prove anything about how life on Earth actually began, and it falls well short of demonstrating that comets somehow delivered life itself. A much stronger and considerably less well-supported claim related to the interstellar panspermia idea discussed earlier. What it does show, fairly convincingly, is that the same broad category of icy, comet-forming material scattered throughout the early solar system, including the material that eventually settled into the Oort Cloud, carried at least some of the basic organic chemical ingredients relevant to life, regardless of whether any of that specific material ever actually made its way to Earth's surface. It adds one more small, carefully verified piece to the much larger, still unresolved puzzle of how life's basic chemistry first came together. Without answering the full question on its own, there's a broader historical pattern worth noticing here, one that stretches back long before Jan, Oort, or Ernst Pick ever put pen to paper. Human understanding of where the solar system actually ends has been revised outward, again and again, throughout the entire history of astronomy, almost every time our instruments or our mathematics improved, enough to see a little further than before. For most of recorded history, going back through ancient Greek, Babylonian, Chinese, and countless other astronomical traditions, the observable universe effectively meant the sun, the moon, 5 visible planets, and a fixed, seemingly unchanging sphere of stars, all apparently rotating around a stationary Earth at the center. That geocentric picture, refined mathematically to a remarkable degree of predictive accuracy by the Greek astronomer Ptolemy, held up reasonably well for well over 1,000 years, not because it was correct, but because it worked well enough, for the observational precision available at the time, to predict where the planets would appear in the sky. The heliocentric revolution, associated most famously with Nicolaus Copernicus in the 16th century and later placed on far firmer mathematical and observational footing by Johannes Kepler and Galileo Galilei, moved the sun into the center and correctly identified Earth as simply one planet among several, orbiting alongside the others rather than sitting motionless while everything else revolved around it. Even after that genuinely radical shift, the known solar system still ended at Saturn, the most distant planet visible to the naked eye, for another century and a half. The invention and steady improvement of the telescope gradually pushed that boundary further outward. William Herschel discovered Uranus in 1781, the first planet ever identified specifically through telescopic observation rather than naked eye tracking. Neptune followed in 1846, discovered not through direct observation at all, but through careful mathematical prediction. Astronomers, having noticed small, otherwise unexplained irregularities in Uranus's orbit, and calculated where an additional, then unknown planet's gravity would need to be located to account for them, before ever actually pointing a telescope at the predicted spot and finding it there. Pluto's discovery, in 1930, briefly extended the known edge of the solar system further still, though its later reclassification as a dwarf planet in 2006. Once astronomers realized it was simply one of many similarly sized bodies within the broader Kuiper belt, rather than a uniquely large outlier, reflected yet another quiet revision of where the meaningful boundaries of the solar system actually lie. The recognition of the Kuiper belt itself as a genuine, populated structure, rather than a purely theoretical proposal, only became solidly established with the discovery of its first confirmed member beyond Pluto in 1992, and its population has continued to grow substantially with every subsequent, more sensitive sky survey conducted since dots set against that long historical pattern. The Oort Cloud represents simply the most recent, and by far the largest, extension of this same repeated story, the edge of the solar system, as understood by the best available science, has moved outward again and again over the centuries. From Saturn to Uranus to Neptune to Pluto and the Kuiper belt, and now to a spherical shell of icy debris that dwarfs everything closer in by a factor of thousands. There is a reasonable chance, given how consistently this pattern has held throughout the history of astronomy, that our current understanding of the Oort cloud itself, its size, its total mass, even its basic two-part structure, will look at least somewhat incomplete or oversimplified to astronomers working a century from now, refined by observational tools and theoretical approaches that don't yet exist. That's not a flaw in the current picture. It's simply how this particular kind of science has always worked. One careful revision outward at a time. There's one more intermediate population worth mentioning, because it fills in another piece of the dynamical picture connecting the inner solar system to these distant icy reservoirs. Between the classical Kuiper belt objects and the long-period comets originating from the Oort cloud, astronomers have identified a population called centaurs, icy bodies currently orbiting somewhere in the gap between Jupiter and Neptune, on unstable, temporary orbits that will, over timescales of a few million years, eventually be perturbed, either further outward, back toward the Kuiper belt, or inward toward the Sun, where they may eventually become active, visible comets themselves. Centaurs are generally understood to be objects in transit, caught partway through a slow, dynamical journey from one stable reservoir to another, neither fully settled in the Kuiper belt, nor yet fully delivered into the inner solar system, a closely related category. Sometimes called Halley-type comets, occupy an intermediate position in terms of orbital period as well, generally taking somewhere between 20 and 200 years to complete an orbit, longer than the typical Jupiter family comets that come from the Kuiper belt, but shorter than the true long-period comets associated with the Oort cloud. Halley's comet itself, fittingly, is the namesake example. The current best understanding is that these objects most likely originated in the Oort cloud, or possibly the more distant scattered disk, a related, less densely populated structure overlapping somewhat with the outer Kuiper belt, and have since had their orbits substantially shortened through a series of gravitational encounters with the giant planets, gradually working their way inward over many thousands of years until settling, for now, into their current, comparatively short, human-observable orbital periods. This entire layered system, stretching from the tightly packed rocky planets, out through the Kuiper belt and its centaur population, through the intermediate Halley-type comets, and finally out to the vast, thin population of the Oort cloud itself, is fundamentally chaotic in the precise mathematical sense of that word, meaning that the exact, long-term orbital path of any individual object within it is, in practice, impossible to predict with certainty far into the future. Even though the underlying physical laws governing the whole system are perfectly well understood and deterministic, tiny, unmeasurable differences in an object's current position or velocity compound over long enough timescales into wildly different eventual outcomes. One comet ejected entirely from the solar system, another settled into a stable, million-year orbit, a third eventually falling into the sun or colliding with a planet, all starting from what would look, at any given moment, like nearly identical initial conditions. This underlying chaos is part of why comet dynamics require the kind of statistical, population-level modeling described earlier throughout Oort's original analysis, rather than any attempt at tracking individual objects across truly long timescales. Pulling all of this together, it's worth sitting quietly with what is actually known about the Oort Cloud and what genuinely remains open. What is known rests on a fairly narrow, though carefully reasoned foundation: the statistical distribution of long-period comet orbits, first analyzed rigorously by Jan Oort and building on Ernst C.P.'s earlier proposal, strongly supports the existence of a broadly spherical reservoir of icy material surrounding the solar system at roughly the distances described earlier. The general formation story, tying the cloud's origin to the chaotic early migration of the giant planets, is well supported by computer simulations that successfully reproduce many other observed features of the outer solar system when run forward from plausible starting conditions. The influence of the galactic tide and occasional passing stars, including the specific calculated future encounter with Gliese 710, rests on solid, independently verifiable orbital mechanics and stellar motion data. What remains genuinely uncertain is considerably more extensive than what is settled. No individual Oort cloud object has ever been directly observed, meaning every specific number attached to the cloud, its total population, its total mass, the precise location of its inner and outer boundaries, the exact ratio of material contained in the inner disc-shaped Hills cloud versus the outer spherical shell, remains a statistically modeled estimate rather than a directly measured quantity. Different research groups, using different assumptions about how efficiently the early solar system scattered material outward, currently arrive at total mass estimates that can differ from one another by a factor of several times over. And there is, as of now, no way to definitively settle which estimate is closest to correct without some form of direct observational breakthrough that doesn't yet exist. The relationship between the Oort cloud and the handful of extreme, detached objects like said, and the broader question of whether an undiscovered massive planet is genuinely shaping their unusual, clustered orbits remains unresolved, likely to stay that way until either a direct detection is made or a sufficiently large, sufficiently sensitive survey definitively rules the possibility out. The exact boundary between the inner Oort cloud and the more familiar scattered disk and extreme Kuiper belt populations is drawn somewhat differently by different researchers, reflecting real ambiguity in the underlying data rather than any simple disagreement over terminology. Even the basic question of how common Oort cloud-like structures are around other stars, while increasingly well supported by debris disk observations and the detection of confirmed interstellar objects like Oumuamua and Borisov, still rests on a comparatively small sample size, drawn from a galaxy containing hundreds of billions of stars. Considerably more observational data likely to come from a combination of infrared space telescopes, large-scale ground-based sky surveys like the Rubin Observatory's ongoing project, and the continued patient cataloging of interstellar visitors as they pass through, will be needed before that broader picture can be considered genuinely well established, rather than merely plausible and consistent with current evidence. None of this uncertainty diminishes how remarkable the underlying achievement actually is: an entire, previously unsuspected structure, one that turns out to define the true physical boundary of our own solar system, and that dwarfs everything else in it by orders of magnitude in sheer volume, was inferred almost entirely from careful attention to the arrival angles of a modest number of comets, decades before any spacecraft had ventured anywhere near the outer solar system, and long before anyone had any real hope of observing such faint, cold, distant material directly. It stands as a genuinely elegant demonstration of how much can be learned about something entirely invisible, purely through patient, careful reasoning about the traces it leaves behind in things we actually can observe. The story of the Oort Cloud also offers a useful, quiet corrective to how the solar system tends to get presented, especially early on in classrooms and textbooks and simplified diagrams. The picture most of us grow up with, a small, cozy, well-lit family of planets circling a friendly local star, isn't wrong exactly, but it is drastically incomplete, describing perhaps 1% of the actual volume our solar system occupies. The remaining 99% is cold, dark, almost entirely empty, and sparsely populated by ancient, unchanged material that has been drifting quietly out there since before the Earth itself had fully formed. Once you know that structure is there, the whole solar system feels less like a tidy, contained neighborhood and more like a small, warm island sitting at the center of an enormous, silent, mostly empty sea. There's a kind of quiet duality in how to think about what the Oort Cloud actually represents for us. In one sense, it functions as a kind of cradle, a protective boundary defining the Sun's own distinct territory within the wider galaxy, holding, in deep freeze, some of the most pristine, unaltered material left over from the solar system's earliest history, patiently waiting for some future mission, someday, to go out and study it properly, whenever the technology finally exists to make that kind of journey feasible in another sense. Considered from the perspective of a species hoping, eventually, to travel beyond its own solar system, the Oort Cloud functions much more like a barrier, or even something like a natural quarantine. Its sheer scale, and the practical impossibility, using anything resembling current or near-future propulsion technology, of crossing that scale within any single human lifetime, or even within many, many lifetimes strung together, imposes a kind of natural speed limit on how far humanity can currently reach, regardless of ambition, regardless of how much any of us might want it to be otherwise. For the foreseeable future, whatever exists beyond that distant shell remains, for practical purposes, out of physical reach, something we can study indirectly, model mathematically, and send small robotic scouts toward, but not something we can visit ourselves, not yet, and not for a very long time to come. And yet, we have already sent something out there, however slowly, however incompletely. Voyager 1 continues its long, silent, one-way journey outward, still transmitting for a little while longer, before eventually falling permanently quiet sometime around the year 2030, and then continuing onward regardless, carrying its golden record, its faded instruments, and its small, quiet testament to human curiosity. Through the vast gap of empty space that still separates it from even the inner edge of the Oort Cloud, it will take several more centuries just to reach that inner boundary, and tens of thousands of years beyond that. Long after every trace of the civilization that built it has changed beyond recognition, before it finally, fully clears the true edge of our solar system and drifts on into the genuine dark between the stars, by then, it will have passed silently through the outer shock of the solar wind, through the quiet, ancient debris of the inner cloud, past countless frozen comets drifting in that same profound emptiness described earlier, becoming, eventually, simply one more small, cold artifact among trillions of others, a tiny metal fossil, indistinguishable at a glance from the icy bodies surrounding it, except for the faint, patient story of curiosity it carries, quietly, into that enormous darkness. It's a strange thing to think about, right at the edge of sleep. Somewhere out beyond everything we can easily picture, past the warm, familiar cluster of planets we learned about as children, there's a vast, cold, mostly empty shell of ancient ice, holding, in careful, undisturbed suspension, material older than the Earth itself, drifting quietly at the true edge of everything we call home. It has been there the entire time, this whole time, patiently waiting, largely unseen, simply because of how far away it happens to be, and how dark, and how cold, and how still. For now, it remains the quiet, distant boundary of everything familiar, the last dark horizon before the wider galaxy properly begins, and the solar system, at last, gently fades away into the deeper dark beyond it. It's worth spending a little more time on how comets, including brand new arrivals from the outer Oort Cloud, actually get discovered in the first place today, since the process has changed enormously since Jan Oort first pieced together his statistical argument using a comparatively small catalogue of historical observations. Modern comet discovery relies heavily on wide-field automated sky surveys, telescopes designed to repeatedly photograph large sections of the sky, night after night, and then use software to automatically flag any object that appears to be moving relative to the fixed background of stars. Surveys such as Pan-STARRS, based in Hawaii, and the Catalina Sky Survey, based in Arizona, have been responsible for discovering a substantial fraction of the comets identified over the past 2 decades, including numerous long-period comets that, once their orbits were carefully calculated, turned out to be making their very first recorded approach to the inner solar system. Fresh arrivals straight from the Oort Cloud. The Vera Rubin Observatory's newly beginning survey, mentioned earlier, is expected to substantially increase this discovery rate once again, thanks to its unusually large field of view and its plan to systematically image the entire visible southern sky repeatedly over the course of roughly a decade, catching fainter, more distant objects than previous surveys were capable of detecting reliably. Once a new object is identified as a probable comet, astronomers around the world contribute follow-up observations, tracking its position over subsequent nights and weeks to refine an accurate orbital solution. That orbital data is centrally collected and catalogued by the Minor Planet Center, an organization responsible for maintaining the official, ongoing record of comet and asteroid orbits used throughout the astronomical community. Once an orbit is well enough established, a newly discovered long-period comet is assigned a formal designation, and its calculated orbital period, that specific number that reveals whether it's on a modest, human timescale path or a truly enormous journey lasting thousands or hundreds of thousands of years, is what ultimately determines whether it gets added to the growing statistical catalogue of Oort Cloud. Evidence that astronomers have been quietly building since Oort's original 1950 analysis. This entire discovery pipeline, largely automated, largely running quietly in the background of modern astronomy, represents a considerable change from the way new comets used to be found for most of history, primarily through careful, patient visual scanning of the night sky by dedicated amateur and professional observers, sometimes competing informally to be the first to spot and report a new object before anyone else. Automated software doesn't get tired, doesn't need clear weather quite as specifically, and doesn't miss faint objects the way a human eye eventually will. And the resulting steady stream of newly confirmed long-period comets continues to slowly, patiently sharpen the statistical picture of the Oort Cloud that Oort and Kepik first sketched out using far more limited data, decades before any of this automated infrastructure existed. All of that quiet, automated searching, all of those careful statistical models, all of those centuries of steadily revising outward where the true edge of the solar system actually lies, eventually circle back to the same simple, calming image, somewhere out past everything bright and familiar, past the planets, past the Kuiper belt, past even the patient, elongated wanderings of objects like Sedna. There is a vast, cold, mostly empty shell of ancient ice, holding, in careful and undisturbed suspension, material older than the Earth itself. It surrounds us completely, from every direction at once, silent and largely unseen, simply because of how far away it happens to be, and how dark, and how cold, and how still it has remained for billions of years. It asks nothing of us, and for now, it mostly waits, exactly as it has for the whole history of everything we've ever built or launched or wondered about. A slow, distant, gently curving boundary marking where our small, warm island in space finally gives way to the wider, darker ocean of the galaxy beyond it. There's also a quieter, more personal thread running through all of this, one easy to miss amid the physics and the statistics. Every single spacecraft currently making that long journey outward, Voyager 1, Voyager 2, New Horizons, and eventually, perhaps decades from now, some future interstellar probe, purpose-built for the task, carries with it a small, permanent record of the moment in human history that launched it. Long after the specific missions, the specific instruments, and even the specific civilization that built them have changed beyond recognition, those quiet, drifting objects will continue outward regardless, carrying that fixed, unchanging snapshot of who we were, into a darkness that will likely remain, for a very long time yet, almost entirely undisturbed.